Okay, so welcome to the Tutte Colloquium. So today we're happy to have Kostya Pashkovich. I think Kostya will join CNO in a month, if I'm correct, of keeping track of when people joining. But I think officially the starting date is July 1st this year. So Kostya obtained his PhD in Magdeburg in Germany, and then he was assistant professor in University of Ottawa, and also research assistant professor in Waterloo here as well. So he's not really new face. So Kostya works on combinatorial optimization and operations research, and he's going to talk about approximability of max cardinality stable matchings with ties. Welcome, Kostya, and stage is yours.
Thank you very much for the introduction. Good afternoon, everyone. Thank you for this opportunity to speak in the Tutte Colloquium. So, as Jane said, I'm going to be speaking about max cardinality stable matching with ties, and the aim of this talk is to show the result we recently obtained for the case when ties are of bounded size. I think many of you are familiar with the problem, but I still will have to define it. So what are we given? So we'll start with the simplest case, which is taught in many CS courses. So it's a case where we don't have ties, really. It's a well-studied and well-understood problem. So what are we given? We're given a bipartite graph with bipartition A and B. So you can imagine that we have students that we have to pair in order to do some exchange program. So we have American and British students, and we need to find one American student and one British student and form such pairs. Okay, so the nodes in the graph represent students, one part American, one part British, and the edges in the graph represent compatible pairs. So what pairs can be potentially formed? A part of the graph structure, we also have preferences. So each student, each node in the graph has strict preferences over their neighbors. So here's an example. You can see a graph with a bipartition. On the left-hand side, we have part A, American student. On the right-hand side, we have B, British students. And the edges in the graph represent potential pairs, the pairs which can be formed. If the edge is missing, like between A1 and B3, you see no edge, it means that such pair cannot be formed. And moreover, you can see that each agent has strict preferences of their neighbors. So with arrows, I indicate preferences. The more arrows there are, the higher ranked is this neighbor for the agent. For example, if you look at the agent A1, agent A1 has two neighbors, and B1 is marked with two arrows, and B2 is marked with one arrow for A1. So it means that A1 ranks B1 higher than B2. So A1 would rather be with B1 than with B2. And similarly for all other agents in this graph. Okay, so that's what we are given. What we are looking for? We are looking for stable matching. So what is a stable matching? So we would like to have a matching in the graph, in the input graph, so that there is no blocking pair. It means we cannot find a one American student and one British student, so that so this notation I used to represent the partner assigned to the agent A in the matching M, and this notation I use to represent the partner assigned by the matching to the agent B. So it should be not true that the partner that we assign to A is strictly less preferred by A than B, and the partner that we assigned to B is strictly less preferred than the partners that we assigned than A. So there's at least one of them is not better off in our matching M than being matched together. So this is called the blocking pair. So let us see what matchings are stable and what matchings are not stable. So in this graph, for example, such a matching, so if we consider such matching, it is going to be a stable matching. So you will not find a pair of agent A and B, so that A is matched worse by the matchings in B, and B is matched worse by the matchings in A. So, and in comparison to this pair, for example, is not, this matching is not stable. So here we have stable matching. Here we have not stable matching. Because if you take a look at the, pair, this one, A3, B2, B2 is matched with no one, so B2 is extremely unhappy, and A3 would be rather matched with B2 than being assigned the current partner B4. So this pair is blocking for this matching. So we have some matching stable, some matching not stable. Okay, so it's known that if we have such an instance, a stable matching always exists, and it can be found efficiently. So that's a famous result by Cable and Shapley, and the algorithm has several core concepts. So the algorithm runs in rounds. And you can imagine that for forming pairs, American students will start to make offers to British students to form pairs. So each American student has one potential offer to give, and each British student can, at any point, accept at most one such offer. And whenever a British student has several offers at hand, the British student has to decide what offers to reject. So this is essentially three core principles of the Gale and Shapley algorithm, and I will just briefly show an example of how the Gale-Shapley algorithm is run. So here we have the instance that we saw before. So we had 4 American students, A1, A2, A3, A4. We have 4 British students, B1, B2, B3, B4. And now American students start to make proposals to British students in turns. Okay, so any American student can start making proposals. So let us start with A2. So we start with A2. A2 would make proposal starting from the top of the preference list. So the preference list of A2 is pretty much simple. It contains only one agent, B1. So A2 will make proposals to B1. B1 at the moment has no proposals, so B1 will accept proposals from A2. And we will have this situation. Okay, so then let us do with next round with A3. So A3 makes proposal to the first person on this student's preference list. So A3 will make proposals to B2. So A3 makes proposals to B2. because there are 2 arrows pointing to B2 and only 1 arrow pointing to B4. So B2 currently has no proposals, B2 will accept it. Okay, then similarly, we can do the same thing with A4. A4 will make proposal to its top choice. So it's B3, so we will get here A4. Okay, so now A2, A3, A4 at the moment have their proposals accepted. They cannot do anything else, but A1 has no proposals accepted. So A1 starts to make proposals, and the first person on A1's preference list is B1. So A1 will make proposal to B1. So A1 will make proposal to B1. At the moment, then B1 gets 2 proposals, one from A2, one from A1, and B1 has to decide. B1 prefers A1 to A2, so B1 will reject A2 and will accept the proposal from A1. So, and A2 will record it also on A2's preference list as being rejected by B1. So at this point, this is a very small example, we will stop the algorithm if every American student either has an accepted proposal or an empty preference list. So, and this is exactly the case. A1 has an accepted proposal by B1 currently. A2 has empty preference list, so we are done here. A3 has an accepted proposal. B2 accepted the proposal of B2. And A4 has an accepted proposal by B3. So all American students now currently are in the situation where they have an accepted proposal by some British student, or their preference, they were rejected by every British student on their preference list. So this is the spirit of the Gale and Shapley algorithm. So I just wanted to remind you of the spirit in which the Gale and Shapley algorithm runs without providing too many details on that. So here, the crucial points for us is that each American student has 1 proposal to offer. Each British student can accept at most 1 proposal, and each agent, like each British student, whenever the British student has several proposals, has to reject some of those. So this is the situation with stable matchings. But what happens when we consider the case of ties? So we still, we have some minor changes. So we still have bipartite graph with 2 parts. So we still have this partition in American students and British students, which would like to be paired for an exchange program. But this time, some of the students might be indifferent between some of their neighbors. So the preference list that they have doesn't correspond to a strict ordering anymore. Some of them might be indifferent. So what do I mean here? So here I made just one change. In the picture of the previous example, you can see that A1 here is indifferent. So everyone else, I kept as it was before, but A1 I made indifferent between 2 options, B1 and B2. So A1 really at this moment does not care whether to be matched with B1 or whether to be matched with B2. So this is what is called ties. So we still can compare any 2 agents, but some of the agents are located in ties. Okay, the concept, the definition of the stable matching remains the same. So we are considering so-called weakly stable matching. So this talk is about weakly stable matching. I just, because we're concentrating only on weakly stable, I'm just keeping it as stable. Okay, so what happens in this case? So in this case, something interesting can happen. So you can see that the matching that we had before this matching, that was stable before, this matching is still stable. So this matching is still going to be stable. Nothing bad is going to happen here. So there is no blocking pair. But there are also other stable matchings. For example, the matching like this is also a stable matching in this instance. So this matching is also stable. And this is exactly what makes the problem interesting, because whenever we don't have ties, if we don't have ties, all stable matchings are of the same size. If we have ties, stable matchings can start to be of different cardinality. Even if the instance is the same, we could have two stable matchings which have different cardinality. Like in this case, we have the same instance, but we have one stable matching of cardinality 3 and one stable matching of cardinality 4. Yeah, so that's exactly what will make max cardinality stable matching problem interesting in the case when we don't have ties. Because if we, if we have ties. If we don't have ties, all stable matchings are of the same cardinality. If we have ties, this can change. Okay, so before going to max cardinality, what is known? So we could still use Gale and Shapley algorithm to find a stable matching. We could potentially just break ties arbitrarily, whatever way we would like to break them, and then run Gale and Shapley, and then you will check that the resulting matching is indeed stable. So existence is really settled already by Gale and Shapley. But if you would like to find maximum cardinality stable matching, then the problem starts to be NP hard. The problem starts to be NP hard. And as with any NP hard problem, we could try to approximate it. So there is a central famous result about stable matchings in the case when we have ties and we would like to find a maximum cardinality stable matching. It's known that we can find a stable matching M that is not too far from the optimum. So it means if we take a look at the cardinality of the stable matching, it's enough for us to boost it, to multiply it, this cardinality by 3/2, and we already get something that is bigger or equal than the cardinality of our optimum. So in the rest of the talk, I will be referring to M as the output matching, like this is, and to opt as the as an optimal matching, so it's a maximum cardinality matching. So this inequality we will also shorten further. We will just say that we can approximate max cardinality stable matching whose guarantees we have. So that's what we mean. It means that we can find a stable matching, so the matching that is stable, and that it's not too small in comparison to the optimum. So if we multiply the cardinality of the output matching by 3 half, we are getting at least optimum. Okay, so what is, okay, so there are, the problem is very well studied. There are very beautiful and nice results. So in this talk, I will concentrate on the problem variant where we have ties of bounded size. So the ties are not becoming too large. So the ties do not become too large. So agent might be indifferent between one pair of agent, another pair of agent, another pair of agent, but it's not possible for an agent to be indifferent like between like 1,000 agents. Like it's the size, the indifference is not too big. So so what is known in this case? So the starting point for this research was a paper by Juan Cancavita, in which they provided approximation guarantee, so approximation algorithm for the case when ties of size at most 2. So every student can be indifferent only between 2 students and 2 other students, but student cannot be indifferent between 3 students. It's not possible to find a student like student A and 3 B students, so that 3 different B students, so that the student A is indifferent between all those 3 students. So we really have ties limited to 2. So in this case, Juan Kanstantsin managed to provide an approximation algorithm for max cardinality stable matching with guarantee 10/7. So the smaller is the approximation guarantee, the better it is fast, because this guarantee, we boost by it our output to exceed opt. So the smaller this number is, the better it's fast. So on the previous slide, we saw that we have an algorithm that provides us 3 half approximation guarantees. So this is 1.5. So Juan Kanstantsin improved it to 1.429 approximately when the ties are not too large. So when all the ties are at most of size at most 2. So as a first step, we took the algorithm, and it was exactly the same algorithm. So it's exactly the same algorithm as Juan Kanstantsin had. And we provided a tight analysis for this algorithm. So we achieved, we showed that this algorithm produces guarantee 4/3. So this is really an improvement. So here it was, they provided algorithm, but have shown only the guarantee 1.429. We took the algorithm and provided and showed that it has guarantee 1.334. Okay, and then the recent result, we were interested really in generalizing that result to the case where the ties are bounded by some number L. So we don't have any more, we are not anymore in the case L equal to 2. We have some L, and we know that all ties are bounded from above by L. And in this case, we provided another algorithm which achieves guarantee like that. So you can see that for case where L is equal to 2, this is exactly 4/3. When L is equal to 2, this is exactly 4/3. And surprisingly, this number coincides with the integrality gap of the LP related to this problem. So this is exactly the integrality gap. But it's not clear to me why it's integrality gap. And it was an open problem where one can provide an algorithm where the guarantee matches the integrality gap. We provided a combinatorial algorithm where we used LP, but not the one for which this is integrality gap, and we achieve this guarantee. Okay, so so this is my, the result which I want to get at the end, but first, let me start with this result. So, so here, we in the case studied by Juan Kanstantsin. In this paper, Juan Kanstantsin studied 2 variants of the problem, and one of them was of ties at most 2. So they changed the algorithm. They changed the algorithm, and the algorithm, in comparison to Gale and Shapley algorithm, had several features that were rather new and surprising. So first of all, they allowed in their algorithm for each American student to make simultaneously 2 proposals. So in Gale and Shapley, each American student were able to just offer 1 proposal. They also allowed each British student to accept at most 2 proposals. So there is not limit 1 anymore, but 2 proposals. So now comes very, like the third part is really, it's very crucial. So whenever a British student has more proposals than 2. So the student has more proposals than the British student has more proposals currently offered than this British student can accept. The British student does not simply reject, like in the Galen-Shapley, this agent would simply reject all the proposals except the most preferred. But the student tries to make 3 operations in this order. And those operations are really a bit surprising. So first operations as a student, the British student will try to make, the student will try to bounce the proposal that to do some bouncing. Then the student would like to do some forwarding, and only if bouncing was not successful, the student would like to do forwarding. If forwarding was not successful, then the student would like to do rejection. So student tries everything possible before rejecting. So everything possible. And this bouncing and forwarding, I'm not going to define them formally, but they essentially contribute to diversifying the structure of proposal accepted. They make sure that proposals are more diversified, like accepted proposals are more diversified among the agents. So it's not possible for agents to break their ties, discriminating some other agents. It's more diverse. Okay. So the third part is really quite important. Then in the fourth part, they also have something which is promotion status, but promotion status was used in several previous algorithms in the field. As far as I understand, it was introduced originally by Kirelli. So in this case, we have 2 promotional statuses. Every American student, while making the proposal, starts as basic. Then when this American student was rejected by every British student on their preference list, the student starts to make proposals again, completely from scratch with the original preference list already as 1 promoted. And then after being rejected already by everyone as 1 promoted, the student tries to make proposals as 2 promoted, and only as being rejected by everyone as 2 promoted, the student stops making offers. So it's not like in the Galen-Shapley, the student stops making offers as soon as the student got rejected by everyone. So here one has to be rejected by everyone 3 tries, like first student runs algorithm as basic, then as 1 promoted, then as 2 promoted. So American students then will have those 3 promotional statuses, and those promotional statuses will help the British students to break the ties. So whenever a British student is tied between 2 different proposals, has 2 different proposals, like one from one American student, another from another American student, and some proposal needs to be rejected, this British student will always prefer American student with a higher promotional status. So promotional statuses help to break the ties. Okay, and then because the structure of the whole algorithm is a bit more complicated, one needed to understand what is going to be the output. So we run some algorithm, 2 proposals here, 2 proposals there, some promotional statuses, but what will be our output? Because clearly in the Galen-Shapley, accepted matching at the end of the algorithm accepted proposals at the end of the algorithm form the matching in the Galen-Shapley case. But in this case, it will be some graph with max degree 2. So it's not the matching. It's not clear that it's going to be the matching. So there is some output criteria. So there is some things that one can output. Okay. So how the analysis of Juan Concavita was working? So they took the matching that was output. Let us say it was M. Took the matching, some matching that is optimum. And then they formed the union of those edges. Okay, except some exceptional cases, we will have passes and cycles. So I mean, unless the edges are repeating, we will have passes and cycles. Some of them will be opt-augmenting, some will be m-augmenting, some will be alternate, like of equal number of opt and m edges. And we will probably have cycles. So each of those, so we will have several connected components. If we depict all our students as nodes, to have a nice image, I stopped having bipartition left and right. I just organize them agents arbitrary on the plane. So, and if we consider m plus opt, we will have some connected components. Some of them are good for us. Like, for example, this connected component, here m has 3 edges and opt has just 2 edges. So here, this connected component is good for us. It shows that actually m is not so bad in comparison to opt if we look at this connected component. But some of those connected components are not particularly good for us. So if we take a look at this one, it's going to be horror. So C intersected with m is equal to 1, and C intersected with m equal to 1, and C intersected with opt is going to be equal to 2. So here we have two, so I forgot to pronounce this, excuse me. So here we have one edge in the matching that we output, and two edges in this connected component, if we consider this connected component, and 2 edges in the optimal matching. So here's the ratio between edges in the matching that we output and number of the edges in the optimum is very bad for us. So we don't really want to have those connected components. So actually, Juan Cancavita can show that there are no such connected components, of length 3. So that was pass of length 3. So they showed that there are no such connected components, which have the ratio 1 to 2. But the next problem for us are components like that. So components like that. So if we consider this connected component, it has 2 edges from m and 3 edges from opt. So this ratio is not so bad as like it was 1 to 2 before. It's 2 to 3, but essentially it will lead, if we have many of those length 5 augmenting passes, we could suffer because we could get closer and closer to the guarantee, which is well known and was already proven by McDermott, Kirali, and Paluch. So if we have many of the connected components that we see on the top, that's going to be bad because we will have to multiply by 3/2 to make the cardinality of m multiplied by 3/2 be at least cardinality of opt. So the good thing is that there are enough of passes, like you see the second from the top, which are longer, to pay for the length 5 augmenting passes. And that is the whole idea. You make, so the idea of Juan Cancavita was to make, to get a charging scheme. So it was a very not trivial charging scheme, from which it was clear that if we have length 5 augmenting length 5 augmenting passes, they will generate some tokens, but for those tokens can pay passes that are of bigger lengths. And if we have a pass of bigger lengths, like for example this one, then here we have 3. It's much lower. It's much lower ratio, like 4/3 is much lower ratio. So the connected components that correspond to longer passes can pay for connected components that are length 5 augmenting passes. So length 5 augmenting passes would push us more towards well-known result, but fortunately there are longer passes that could pay for that. And that was the idea of Juan Cancavita. The charging scheme was quite not trivial. It was very detailed and quite non-trivial charging scheme from which follows that everything works and longer passes can pay for shorter passes. Okay, but that was, for us, it was hard to deal with. It was hard to deal with. So we wanted to have some more local charging scheme, because in their case, they had passes that were running through the whole graph and so on and so on. So it was not easy for us to manipulate this. So we considered a more local charging scheme. So what was it? So as Juan can the main reason for us, the main object to work with in the proof was the proposals that got accepted at the end of the algorithm. So the algorithm runs in several passes. American students can make proposals. Each American student has 2 proposals to offer. Each British student can accept at most 2 proposals. And there are many proposals that get accepted in the end of the algorithm. Only some of them you see on the picture. You see only the proposals that were included in the output matching M. But in reality, there are more proposals. There are more proposals than that that should be in the picture. And there are proposals that were neither counted for in M and not participating in opt. So this is exactly the proposals that I added as red lines. And they should be matched. So for example, here you can see only, you can see that this agent got some holds one more proposals than that of this, but we don't see from which agent or to which agent this proposal was made. So we still have to match some of those proposals together. So we still have to form some matchings, and sometimes it's becoming difficult for us to match those parts. And this is the whole essence of the charging scheme. Okay. So what did we do with Robert? So I just kept this picture from before on the top. So we had our matching M's that we output. We have optimal matching, and except the edges in M and opt, we also have some proposals that were accepted at the end of the algorithm. So far, so good. Okay, so each of the proposals that are marked with like this red curve, we will call them good or bad. They will start to becoming good or bad. For each endpoint, they are either good or bad. So endpoint A decides whether this red proposal is good for it or bad, and endpoint B decides whether this proposal is good for it or not. So if we have such a proposal A and B that was accepted at the end of the algorithm, but didn't appear neither in opt nor in M, it will start to have the characteristic of good and bad, and it's going to be for A and independently for B. And bad means that it's hard for us to match it with another bad. Okay, so the key feature, like in this whole our idea, was that the same proposal cannot be bad. Like, so if we have one curvy red proposal, it cannot be bad for both endpoints. It cannot be bad for A, and it cannot be bad for B. So we will see how do we use it. And then we construct the charging scheme. We will start to give each agent the cost. So if we have an American student, the cost of the American student will appear as follows. We go through all proposals that got accepted by this American student at the end of the through all proposals of this American student that got accepted at the end of the algorithm, and do a summation. If we come across a proposal that was bad for this American student, we add 2. Otherwise, if it comes through other proposals of this American student that was accepted at the end of the algorithm, we add 1. And similarly, we consider the cost of the British students. We go through the proposals that they accepted at the end of the algorithm. If we come across a good proposal for this student, we at 0. If it comes to a proposal of some other proposal, we add 1. Okay, so now I copied this whole thing here. So from the fact that the same curvy red proposal cannot be bad for both its endpoints, we can get very simple inequality. So in the box, you just see what I copied from before. It's not so it's only that this curvy red proposals either good or bad for its endpoints, and there's a definition of the cost. Okay, so we get this inequality, and this is the main thing. So if we go through all proposals and count how many proposals do we have. So this is just counting how many proposals do we have and multiply by 2, accepted in the end of the algorithm. This is just if we go through all proposals and sum 2. But how much does each proposal contribute to the cost of the students? How much each proposal contributes? So if we have a proposal that is not a curvy, if we have some proposal acceptance and observers that is not this red one, so it's either appearing in M or opt, then the corresponding American student will get 1 and the corresponding British student will get 1. So such proposals that appeared in M or opt in total will contribute only 2, so we are fine. If we have a proposal that is curvy red, then the only way for the curvy red proposal to contribute to the total cost more than 2 is to appear here and appear here. But for curvy red proposals, it would mean that it's bad for both of its endpoints. So it's not possible. So essentially, the fact that proposals cannot be bad for both endpoints are important for getting this inequality. Okay, so we will get this inequality. Just inequality. This is a picture from before. With what are we working? We're comparing M and opt, and some red proposals are still there, and they got acceptance end, but didn't appear in M and opt. So then we need some more inequalities to obtain the approximation guarantee. The second inequality that we needed is quite simple. I'm not going to explain it. This is this follows from the rule by which the output is constructed. So the cardinality of the output matching is at least 1/2 of the total number of proposals that were accepted in the end of the algorithm. And there comes the third inequality. That's really the whole core of the paper. The third inequality is really the most complicated part. So it's the whole core of the paper. So if we sum through the cost of all American students plus sum through the cost of all British students, we get at least 3 times that. So if we combine this whole together, so this allows us to compare M to 1/2. So it means if we multiply M by 4, we get at least this. So from 1 star and 2 star, we get that 4 times M is at least this. So we get this inequality. But on the other hand, the inequality 3, which is the whole center of the paper, is leading us to the fact that then 4M, which is bigger than this, and this should be bigger or equal than this 3 times opt. So, and we get the needed guarantee for 3. So let me, so here I'm not presenting this part. Let me just briefly say how is it obtained. So this inequality, so this is the whole center of the paper, as I said. So it's obtained essentially by showing slowly that for each connected component in this graph, so if we consider this graph, for each connected component C in M plus opt, we have that the sum of the cost of American student in this connected component plus sum of the cost of British student in this connected component is 3 times the number of edges from the optimum in this connected component. So then you can just sum over all connected components and obtain this inequality when you do the summation through all connected components. So, so essentially this is the one which take the whole time. Okay, that was the result with Robert, and this gave us possibility to show 4 with 3. So let me then show the recent result with Johan Penneman and Natik to fix it. So the algorithm is obtained by modifications from the algorithm of Van Contervita. I guess some of the modifications are ones you might expect. So we are working in the case where instance has size at most L. So this time, each American student has at most L proposals. Each British student can accept at most L proposals. And the whole bouncing forwarding rejection starts only when British student has more than L proposals. The promotional status does not change. So the real thing here in the update of the algorithm, even so that there's more or less one concatenate algorithm, so it's to be clear about bouncing, forwarding, and rejection, because there are several ways to define it. One needs to define it well. And then construct the output. So this is the only place where we needed linear programming in this case. So we run the whole algorithm, and we needed linear programming only in this case. So here we don't work really with linear program which integrality gap I mentioned, have some completely different linear program, but surprisingly we match the integrality gap of the standard of P for the problem. So what do we have then for this thing? So what do we have in the analysis? So first part of the analysis, so this is, I again copied what we had from before. So what did we have in the analysis? So this one follows in a similar way as before. Even so, here one has to be very careful, because we needed to completely redefine what is good, what is bad, because good and bad definitions didn't work for this proof. We needed to change it. Then we needed this inequality. So 1 and 2 are more or less done in completely similar way. So it's only here technical thing is to make sure that definition of good and bad works. But what needed a lot of work is again the third inequality. Sorry, the third inequality is the one which needed a lot of work. And here the inequality looks a bit different than before. I will show how to obtain it. Now, so as in the case with Robert, whenever we combine all 3 inequalities, we get what we needed. Because if we multiply this by 2 times L, we get that this by 2 times L is at least this. And then we can compare this to this. And then if we bring everything on related to M on one side and everything related to opt on another side, we get exactly the inequalities that we want. We get that 3L minus 2 times M is bigger or equal than 2L minus 1 times opt. But let me just show how this the third inequality is shown, because this I'm not going to be able to show in detail because it's really the most technical part of the paper. But I will be able to give an intuition what was not so straightforward for us with Robert to generalize it. So not surprisingly, so we want to show this inequality. Not surprisingly, if we go through connected components as before, we can show that sum of costs of agents in the connected component is bigger or equal than L plus 1 times the number of edges from opt in this connected component. So that was not really such a surprising fact. But the analysis didn't work. It was clear that the analysis will not work. So here, the whole idea, like if one considers this inequality, to charge the cost of the agents to the edges, more like to charge, maybe it's otherwise, like edges in the opt to the cost of the agents. But it does not work. The analysis simply doesn't work, and it was clear for us that we will not get anything, no improvement in the guarantee. Even so, this inequality completely corresponds to the ones that we saw for the case L equal to 2, because for L equal to 2, here just 2, 3, and this was fine. Okay, so here one needed more work, and one needed first of all to get a clear idea what do we need. So it wasn't enough for us to claim that for connected components, this holds, but we also needed to say that if the connected component was an augmenting path, so it was M augmenting path, so the number of edges in opt in this connected component was larger than the number of edges from M in this connected component, then we also had an additive penalty. We had that the inequality held not only with the right-hand side from L, but with plus L minus 2. And of course, from the case when L was equal to 2, we didn't know, we didn't need it, but yeah, it took some time to understand that we need something here. And so proving that is the whole really the main part of the proof. But after we have it, we can get the inequalities that we want. So we wanted to have this inequality, so we can do again summation over all connected components. We can do the summation over all connected components. And each time we encounter a connected component, we get at least L plus 1 times the number of edges from opt in this connected component. But whenever we encounter an M augmenting path, we also have additional summoned L minus 2. So how many times do we encounter an M augmenting path? So we will encounter an M augmenting path at least the cardinality of opt minus cardinality of M, because each augmenting path can make opt just by 1 higher. So if we have cardinality of opt minus cardinality of M, at least so many times we will encounter M augmenting path in M plus opt. So in this gives us required inequality. So I'm leaving the whole core out. So this is the whole technical, this is the core of the paper, and that I'm not really showing. I'm just showing that. Okay, so so this is the result, and so far it's really the best that at least I'm aware of for the bounded sizes. Types of bounded sizes. There are other great results, but they have further restrictions on the structure of the ties. Like only American students, for example, have ties, or like they have additional structure. In the general case, where we have only the upper bound on the size of the ties, this is the best approximation guarantee of which I'm aware of, and this matches the integrality gap of the standard LP for the problem. Okay, so what concerns the inapproximability results? So what concerns inapproximability results? So the currently best, I'm going to omit NP hardness results. So I'm going to speak only about UGC hardness. So it's not surprising that the result is even better. So with respect to UGC hardness, we know that we cannot approximate the problem with guarantee better than 4 over third minus epsilon. And this holds even for the case when the ties are of size at most 2. So you can see that for the case L equal to 2, it means that our result cannot be improved unless you disprove UGC conjecture. Okay, so but that's also best known inapproximability result in the general case. So 4/3 is the best inapproximability result. So, and this result is constructed on the instance where ties are of size at most 2. So I don't have much time. So let me just briefly sketch how the result of Yanagisawa works. So result of Yanagisawa, so it's not, yeah, so if we speak about UGC hardness, one of the great problems to try to reduce would be probably minimum vertex cover problem, and that's a problem that Yanagisawa is reducing to stable matching. So, and he considers specific case of graph. This allows him to actually do some smart, some better analysis. So he considers vertex cover in the graph where there is perfect matching. This allows to save at some places. So and then for each edge in this perfect matching, Yanagisawa introduces such gadgets. So this is for each edge in the perfect matching. So this is for each edge in the perfect matching. Yanagisawa introduces such. So if we have an edge ij in the perfect matching in this graph, Yanagisawa would introduce such a gadget for it. And then the technical part is to show that I'm not describing the whole preference list. So here I'm just giving intuition for the construction. So here the main technical difficulty is to prove then the maximum cardinality stable matching in the graph constructed by Yanagisawa is equal to 5/2 times the cardinality of the node set in the graph from which we're using vertex cover times vertex minimum vertex cover for this graph. And this gives the opportunity to prove 4/3. So this gives the opportunity to prove 4/3 because in the case when vertex cover is almost the whole node set, minimum vertex cover is almost the whole node set, we have that maximum cardinality stable matching has cardinality at most 3/2 of the
yeah, sorry, I didn't want to be rude, but if you can wrap up in about 1 or 2 minutes, that would be very helpful.
Okay, thank you very much for, thank you, sorry for going over time. Okay, so, and in case when the vertex cover is, minimum vertex cover is is roughly 1/2 of the nodes, we get something like that. And then from dividing this 2v by 3v, 3/2v, we get exactly this 4/3. So this is the whole idea of this 4/3 if one presents it this way. So yeah, so we'll wrap up, but so here the way we can so here, this constant, we cannot really improve better than 1 unless we have some conceptual new ideas, because here, yeah, so here, stable matchings in instances with ties change very continuously. So if we have stable matching of size 5 and 7, they will start, there is also stable matching of size 6. So there's really not yeah, one needs some new idea to get here some constant better than 1. I mean, one needs some new ideas. Maybe one can save here. Yeah, here I'm not sure. So yeah, so and this is I would say the main open problem for these instances to prove better in approximability results than 4/3. So I would guess this is the main open problem here, that whether this can be improved, the result of Yanagisawa can be improved, and whether one can show that the best known approximation guarantees are the best possible. So up to UGC. So whether one can improve it to 3/2 minus epsilon. Okay, so that's, yeah, but one needs to change the gadgets. If you analyze the gadgets has ties of size 2. So our result shows that the ties needs to get larger and larger and larger. How to construct them, how to use them, is not really clear. Yeah. Okay, so thank you. I will finish here with open problem to improving this thing to 3/2 minus epsilon.
Well, thank you, Kostya, for the nice talk. So yeah, it's a bit after 4:30, so let's just see if we can get some quick questions from the audience. So Joseph Cherian has a question here. What if L, this is allowed, I guess the tie size is non-constant? Can one rule out big O1 approximation ratio via harness of approximate results?
So let me just. Could you
okay, Kasia, I'll just say it. So the question is, what if those, so basically I'm asking, are there any cases of the problem where a non-constant hardness of approximation has been proved already or is provable?
Non-constant hardness of approximation. Sorry.
So the thing is, the indifference lists, you are assuming that these are of bounded size, right? But yeah, suppose we have very large indifference lists.
So this result will still, okay. So if you don't, so this means, yeah, thank you for the question. Yeah, I probably, yeah. So this means that even if you restrict yourself, so this result holds in general. So what I wanted to say is, even if you restrict yourself to the ties of size at most 2, this will hold. But this result holds in general, really.
Right, but my question is about non-constant hardness. So does that make sense? I mean, suppose you have very huge indifference lists, and
so the upper bound is 3/2. Sorry, I might. So
oh, I see. So you're saying upper bound. Wait. Upper bound of 3/2 holds also for unbounded indifference list, is it?
Yeah. So this result by multimetrically, this holds for any case. Like so.
Okay. Thanks. Yeah, I missed that. Thank you.
Okay.
Thanks.
So we can leave more discussions in the informal chatting time. So let's unmute ourselves, and thank you, Kostya, for the nice talk.
Thank you very much for the.
Thanks.